Once the recording starts, no, we'll start the problem. Okay. Okay. So the third problem on Francis now. I told you yesterday, whenever you attend a problem on Francis, he will use the term inlet diameter, outlet diameter, external diameter, internal diameter. Don't go with these terms. So directly go with the values. So 1.2 meters and 0.6 meters are the diameters given. So larger one will be D1. No confusions here. Okay, it is very much clear. So larger value you have to take it as D1 and smaller value you have to take it as D2. So that is the first thing given. The head on the turbine is 22 meters. So total head available is 22 meters, which I am writing now. Next, the velocity of flow through the turbine is constant and equal to 2.5 meters square, meter per second. So what is this velocity of flow? So velocity of flow is nothing but Vm. He says it is constant throughout, therefore Vm1 is equal to Vm2, which is equal to 2.5 meters per second. So I'll update the value here as well. So this is equal to 2.5 meters per second. Okay, that's great. Now the guide blade angle is 10 degrees. Now what is this guide blade angle? If guide blade angle is 10 degrees, what is this angle? So it becomes the angle through which the water is striking the blade. The guide blade angle is nothing but it is an angle through which water is striking the blade. So that's why. What is this 10 degree I am asking you? What is this? Anyone? Here he says the guide blade angle is 10 degrees. Alpha 1, exactly. So it is alpha 1, which is equal to 10 degrees. And the runner vanes are radial at inlet. So usually the Francis turbine, if he gives the problems on Francis turbine, as well as in case of a Kaplan turbine as well, remember outlet is always radial. Outlet will be just a right angle triangle like this. Okay, no need to get confused here. In the Francis turbine, in Kaplan turbine, outlet is always radial. In this particular problem, he says even it is radial at the inlet. That is why I have drawn even the radial at the inlet. Okay. If the discharge at the outlet is radial, so he has given directly that discharge at the outlet is radial. Determine. So what we need to find here? To find number 1, speed of the turbine. That means N is being questioned. Okay. Next, vane angle at outlet of the runner. Can anyone say what is this? He is asking us vane angle at outlet of the runner. What is need to be found out? Vane angle at the outlet of the runner is the second question that we need to solve for. Very good. It is beta 2. Beta 2. Okay. Next, third one. Velocity triangles at inlet and exit. Already we have drawn velocity triangles. So third one is velocity triangles we need to draw. That we will be taking care of. Fourth one is the hydraulic efficiency hydraulic. So this is the problem given. So now we know that all these values, if you see here, I will just write once again. Vm1 is equal to Vm2. All these values are nothing but 2.5. So V1, VR1, V2, Vm2, all these values are 2.5. Now alpha 1, I know it is 10 degrees. First, we shall try to calculate the value of the turbine speed. So any idea through which I can calculate the turbine speed? I should calculate first. I should calculate to find step 1 I would take. Step 1, N is being questioned. Any idea? So N where it comes in U. So U1 is equal to pi D1 N divided by 60. So by some chance, if I found the value of U1, Since I know the value of n, I will be in a position to calculate what is d1. Simple. So I have to calculate u1 first. So how do I calculate u1? Come to the velocity triangle here. Okay, alpha 1 is known 10 degrees. This length you know, which is 2.5. So I can calculate u1, isn't it? I can calculate what is u1. So what I should do for that? I should apply tan alpha 1. So tan alpha 1, if I apply, opposite is Vm1 divided by adjacent is u1. So from this, u1 is equal to Vm1 divided by tan of alpha 1. Now substitute the values. Vm1 is 2.5 divided by tan of alpha 1 is 10 degrees. So from this, what is the value of u1, guys? Very good. So 14.17 is the value of u1. Now, once the u1 is calculated, I can use this formula. So 14.17 is equal to pi into d1 value was 1.2 into n divided by 60. So from this, what is the value of n I am going to get? So whatever I get, that would be in RPM. Okay, 225, that's correct. 225.52 RPM. So the first step is now done. Second is to calculate the value of beta 2. So how do I calculate the value of beta 2? Now I will refer here back. So I need to calculate the value of beta 2 now. So this is being questioned. I know this length, which is 2.5. So I guess I can calculate u2, which is pi d2 n divided by 60. Since I have calculated n, I can calculate u2. So once u2 is known, you can apply tan to calculate the value of beta 2, and that is how it is done. Okay. So let us come back to the equations now. So beta 2 has to be calculated. For that, first you need to calculate what is u2. u2 is pi d2n divided by 60, which is equal to pi into d2 is what? d2 is 0.6 into 225.52, this whole divided by 60. Can I get the value of u2, guys? Very good. 7.08 is the value of u2. Now, in order to get beta 2, I would apply tan beta 2. So tan beta 2 is opposite, which is Vm1 divided by adjacent. Just a minute. Okay. Are you able to hear me, guys?
Yes, sir.
Okay. So we'll continue the problem. Tan beta 2 is opposite VM1. Adjacent is U2, I guess. Okay. Fine. So now from this, beta 2 is equal to tan inverse of VM1. VM1 is how much? 2 point, something was the well left, 2.5 divided by U2 is 7.08. That is equal to, yes, correct. The value was 19.448. Okay, so the second bit is done. Third one is the velocity triangle. We have already drawn it. So velocity triangle is done. Let us go with the fourth one, where we need to calculate the hydraulic efficiency. Now, you guys know the formula for hydraulic efficiency, I guess, right? We have used it. It is there in the design parameters as well. It is U1, VU1 divided by G into H. Very, very simple. So U1 and VU1 both are same here. So it is 14.17 into 14.17 divided by 9.81 into 22. So what is the hydraulic efficiency, guys? 0.93. Very good. So hydraulic efficiency is 93%. Okay. So that is the problem. So you can write the result that this turbine has hydraulic efficiency of 93% with N is equal to 225.52 RPM and beta 2 equal to 19.44 degrees. So this type of result you have to write for every problem. That will increase your marks. Okay, increase your clarity. When the evaluator is evaluating, if he sees this result statement, if you directly put like this and give the mark straight away. Okay, he will not even look into your wrong and rights. So always have a habit of writing the result statements. Okay, next we will move on to the problems on Kaplan turbine. So the wonderful thing about the module number 4 is the Francis and the Kaplan turbine both have same velocity triangles. Absolutely no change here and there depending upon the value of VM1. This should be changing. Okay, for example, the velocity triangle might come like this. Okay, so VR1 would be like this. Okay, in some cases when U1 is lesser than VU1, such things happen. Okay, apart from that, everything would remain same. Okay, so shall we try to solve this problem on Kaplan turbine now? Kaplan turbine. Okay, now data given data. Given data. Okay. The Kaplan turbine has an outer diameter of 8 meters. Outer diameter, I told you. Okay. So outer diameter. That is D naught, which is equal to 8 meters. And inner diameter. Be careful about the diameter here. Inner diameter, which is dB, 3 meters. Why it is called as dB? Because it is also known as the boss diameter. Inner diameter is also known as the boss diameter. Okay. Next step. Developing a power of, so power is being given 30,000 into 10 to the power of 3 watts. That is the power output from this turbine. Running at a speed of 80 rpm, so speed is being given, which is 80 rpm. Under a head of H is given, which is 12 meters. The discharge through the runner is, so Q value is being given, which is 300 meter cube per second. Okay. Next, hydraulic efficiency is given. Efficiency hydraulic is equal to 95%. So what we need to find here? So to find first one, inlet and outlet blade angles. So that is beta 1 and beta 2 is question. Second one, mechanical efficiency. Third one, overall efficiency. So all these things you need to find here. Mechanical efficiency and overall efficiency. Let us start with the solution. Okay. So first we will try to find out beta 1 and beta 2. So how we are going to do it? Okay. 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 Now let us try to calculate U1 first. U1 is sir. Done. Okay. So U1 is equal to where was I? So it is pi D1. D dot is nothing but D1. Okay, this is nothing but D2. So it is pi D1 N divided by 60. So here it is pi into 8 meters into 80 is the speed divided by 60. Can I get the value of U in meters per second? Very good. It is 33.51. So once I have got the value of U, now I can use the hydraulic efficiency formula. You know it is given by U1 VU1 divided by G into H. From this I can get the value of VU1. How? Substitute. 0.95 is equal to U1 is 33.51 into VU1 divided by 9.81 into available head is 12 meters. So from this, what is the value of VU1? Okay, 3.33 meters per second. Now, always remember, inner diameter is also called as boss diameter, and even it is also called as hub diameter. In few of the problems, if it is mentioned as hub diameter also, that we have to take it as the inlet diameter. Okay, fine. VU1 is done. Okay, next step. I will just write down whatever I have calculated here. I guess I have calculated the value of U1. How much it is? 33.51. VU1 I have calculated. It is 3.33. Okay, so this much I have calculated now. Anything else is given in the problem? I guess nothing is given. Okay, fine. Okay. Next. So you can use, to find a VF1, you can use the formula of Q. So Q is given as pi by 4. A into V, no? It is pi by 4. A is pi by 4 d naught square minus dB square. So outer diameter and the boss diameter or hub diameter into velocity, which is nothing but Vm. Okay, velocity is nothing but Vm1. So this is the discharge formula. So I would mark this rather and say need to be remembered, and it is in design formulae of Kaplan turbine. So it is in design formula of Kaplan turbine. So from this, Q value is 300. I hope it is 300. 300 meter cube per second. That is equal to pi by 4 into d naught square is 8 square minus dB square is 3 square into Vm1. So from this, what is the value of Vm1 you are going to get in a meters per second? Very good. Thank you, Manish. How much it is? 6.94. So immediately I would update here. So Vm value is 6.94. Now I have got the values of the length BC as well as this length. I have got this length and I have got this length. So I can calculate the value of beta dash by applying tan of beta 1. So that is what my next immediate step would be. Okay. Back here, let us now apply tan of beta 1, which is equal to, so opposite is Vm1 divided by, I can write U1 minus of Vu1. So beta 1 is equal to tan inverse of 6.94 divided by 33.51 minus 3.33. What is the value of beta 1? Okay, 12.95. Very good. So beta 1 value I have calculated. Next we will go to beta 2. So in order to calculate beta 2, it's very simple. So always you remember this, Vm1 would be equal to Vm2. So in that sense, even this particular value is also 6.94. Okay, and you can even say that U1 would be equal to U2. In that sense, this particular value is also how much? 33.51. Okay, so taking that into consideration, what I can do is I can now immediately apply tan beta 2. If I apply tan beta 2, opposite would be Vm2 divided by this thing is U2 there. Okay, and one mistake I have done, guys. So all the thing what you have written, all this Vm is Vf, not Vm, because Kaplan turbine is a axial flow machine. For radial flow, you are supposed to use Vm. For axial, you have to use Vf. Okay, so I'll just change all this to Vf. I forgot I'm directly doing the problem. Vf. Anywhere else? Here. So this is Vf. Beta 1, U1, Vf1. Okay, done. So even in the velocity triangle as well, this is Vf. Because it is axial flow machine, and that is why your U1 would be equal to U2. Okay. Okay. Now, so that is equal to beta 2 is equal to tan inverse of 6.94 divided by 33.51. So that is equal to how much? 11.7 degrees, I guess. Correct? Correct. Very good. That is the value of beta 2. Now, how will you find step 3 or step 2 to find the mechanical efficiency? So mechanical efficiency is nothing but shaft power divided by power by water, or I would say power by water to runner. Okay, so now shaft power, it is already being given, which is 30,000 kilowatts divided by power by the water to the runner is given by rho kev u1 vu1, and say that you have to remember this. Okay, need to be remembered. Okay, so again it is present in design formulae. Okay, if you of course closely observe the mechanical efficiency formula, point number 5, hydraulic efficiency is given by so and so, mechanical efficiency is given by so and so. There he has clearly mentioned that the power of the water to the runner must be taken as rho cube u1 and vu1. Okay, so substituting the same thing, how much you will get? It is equal to 30,000 into 10 to the power of 3, this whole divided by 1000 into 300 into 33.51 into 3.33. Very good. So it is 0.89, which is equal to 89%. So this is your mechanical efficiency. Okay. Now, last one to find overall efficiency. So how will you find overall efficiency? It is very, very simple. Overall efficiency is the product of mechanical efficiency and hydraulic efficiency. Okay, so we have to remember this again. So that is equal to mechanical efficiency is 0.896 cross hydraulic efficiency is 0.95. So what is overall efficiency? Okay, so it is 0.85, or I can say 85% is the overall efficiency of this particular turbine. And there ends your problem. Okay, so I'll try one more problem on Francis turbine and stop the class. Okay, so the next immediate problem is this one. Propeller turbine has an outer diameter of 4.5 meters and an inner diameter of 2 meters. So outer diameter, I told you, outer diameter is nothing but d naught, which is equal to 4.5 meters. Inner diameter is also called as hub diameter or boss diameter. So this is dB, which is equal to 2 meter, and it is also equal. It develops the power of 20605 kilowatts of power, and the head of 20 meters at a speed of is 0.94. Overall efficiency is 0.88. Everything he has given, what we need to calculate them. So to find runner blade angles, again in beta 1 charge through the runner. So Q here first. Very simple problem. Very simple problem. Okay. So let us try to solve this. Very easy. Solution. Okay. Now, he has given the hydraulic efficiency, which is nothing but U1, VU1 divided by G into H, correct? And U1 is equal to U2 is equal to U, you can calculate as pi d naught N divided by 60. So that is equal to pi into d naught is 4.5 and N is 137 divided by 60. So what is the value of U you are going to get? 31.8. Okay. 32.27. Okay. 32.27. Okay. So now again same thing, substitute here. 0.94 is equal to U1 is 32.27 cross VU1 divided by 9.81 into available head is 20 meters. So from this, what is the value of VU1 you are going to get? 32.27. Correct, Anish. VU1. Same, the procedure remains same for almost all the problems. Okay, so VU1 is 5.71 meters per second. Once the value of VU1 is calculated, we can use tan beta 1, isn't it? Okay. Okay. So we have to calculate. See, the thing is, in order to get beta 1, we will apply tan beta 1. Tan beta 1 is what? VF1. Again, I will change here. It is VM. This is VF. Even this is also VF here. Okay. Now, what is tan beta 1? Tan beta 1 is VF1 divided by U1 minus of VU1. Of course, you know the value of U1 and the VU1, but you don't know the value of VF1. No, you cannot calculate. If VF1 has to be calculated, as in the previous problem, you were using pi by 4 into d naught square minus dB square into VF1. If Q was given, here Q is also not given, isn't it? Q is also not given. So in such cases, what you have to do, he has given one more beautiful parameter, which is overall efficiency. Okay, you have to pick that particular value now. So what is overall efficiency? Overall efficiency is equal to, you know this already, it is shaft power divided by water power. So shaft power he has given, which is P, and over water power is rho G, Q, and H. Okay, so overall efficiency is how much? 0.88. 0.88. Shaft power is how much? 20 something he has given now. 20605 into 10 to the power of 3 divided by 1000 into 9.81 into Q you are supposed to calculate. At head available is 20 meters. So from this you are going to get the value of Q. Okay, so what is the value? Okay. Q value is 119.34 meter cube per second. Good. So once I have got the value of Q, I can calculate the value of Vf1. So take Q is equal to pi by 4 d naught square minus dB square into Vf1. So Q is 119.34, that is equal to pi by 4 into d naught is how much? 4.5 square minus 2 square into Vf1. So from this, I would get the value of Vf1. It is a value. Okay. Vf1, which is equal to 9.35. You know very clearly that Vf1 is equal to Vf2, that is equal to 9.35 meters per second. Now, once you have got the value of Vf1, you can use tan beta 1 and beta 2. Now the things becomes easier. So now you apply tan of beta 1. So if you apply tan of beta 1, opposite is Vf1 divided by u1 minus vu1. So from this, beta 1 is equal to tan inverse of 9.35 divided by 32.28 minus 5.71. So from this, what is the value of beta 1 in degrees? Okay. So that is beta 1. So now beta 2 we can calculate by applying tan as well. Tan beta 2 is equal to Vf2 divided by u2. Okay. Now this is beta 2 is equal to tan inverse of 9.35 divided by 32.28. So from this, what is the value of beta 2? 9.35 is what, Manish? Beta 1? Or 9.35 is Vf1, okay. Calculate it. 19.38, correct? So 19 point, so this is 19.38 degrees and okay, 16.15. So these both are inlet blade angle and outlet blade angle are calculated. Okay, next you have to calculate the value of Q, I guess. Q is already been calculated. Q is 119.34 meter cube per second. Just highlight this. Anything else that need to be calculated? Only two parameters. Okay. So I would write the result for given propeller inlet and outlet blade angles were found to be 19.58 degrees and 16.15 degrees with a flow of 119.34 meter cube per second, and there ends your problem. Okay. So any difficulty in solving these problems? I guess after solving complex problems in your module number 2, these problems will be really easy, I hope.